Well, welcome, chemistry friends. We're picking up our lessons from Chapter 17, Carboxylic acids, esters, and amides, focusing on 17.6, the acidity of carboxylic acids. In the notes that we are taking, we're about 3/4 of the way down on the 9th page of the packet, just so you can see the expectation for notes. So we're going to go back a little bit to the perhaps the last chapter you had from first semester on acids and bases. And here we can see that a carboxylic acid indeed has the word acid in its name. We have to remember what that means in terms of definitions for acid and base chemistry. Excuse me. We know from the definition of an acid, acids are proton donors. And what that means in terms of a Bronsted-Lowry acid-base theory, the Bronsted-Lowry theory, and bringing back a little bit of first semester, defines an acid as a proton donor. And if you hear the word proton, I want you to just think of that as the hydrogen ion in that formula. And of course, the proton has to go somewhere, so we defined the base as the proton or hydrogen ion acceptor. And with Bronsted-Lowry theory, we form what are called conjugate pairs. So let's review that concept a little bit as well. The Bronsted-Lowry conjugate pair general formula is written here. We have a carboxylic acid, and right here is the proton acid in a carboxylic group. Remember the functional group, C double bond O, O, H. That's a carboxylic acid, where this is the proton, the hydrogen ion that is transferred during an acid-base reaction. Recall water is written as HOH, and it has these electrons on the oxygen, making it very electron rich. So if this is a very negative region on the water molecule, and this is a very positive region, a positive proton, we can see a proton transfer occurring, and that's exactly what happens. The oxygen reaches out for that proton and takes it from the carboxylic acid. We form on the product side after the proton transfer, and let me just remind us that that's what acid-base chemistry is all about, is a proton transfer from the acid to the base. And now look at what's happened. The carboxylic acid without its proton is now an anion, a negatively charged ion. That's how I remember that vocabulary word, is a negative ion. And I can see the negative charge where the proton once was. And of course, this now is called the hydronium ion. It is the acid ion, often called protonated water. Oops, I forgot the R. Protonated water. Simply because it has an extra hydrogen. And so its structure, of course, now with 3 hydrogens and 1 set of lone electrons gives it a +1 charge. The conjugate pairs are those that only differ by a hydrogen ion. This acid formed its conjugate base. This base formed its conjugate acid. So we're looking at acid-base chemistry in just a general way of looking at Bronsted-Lowry's, but specifically with the carboxylic proton there on the OH part of Cu. So they're very weak acids comparatively to like hydrochloric or sulfuric acid, but nonetheless, they do have an ionizing potential. So when I think about what a small percentage might mean in terms of this arrow, perhaps a better visual is to say a weak acid partially ionizes, maybe like 1% of the molecule, and 99% of it stays in the molecular form. So it's somewhat successful at ionizing. That's the term weak. It only partially ionizes. So if we have these carboxylic acids, and they are indeed acids, we know that they react with a base in a neutralization reaction. Carboxylic acids react with bases to form a salt. So let me remind you again, just from acid-base chapter, semester 1, when an acid reacts with a base, the general formula says we make a salt plus water. So let's take a peek at the salt that would form with a base called sodium hydroxide. Sodium hydroxide is a base because it has the OH negative ion. Now think of this general pattern. Let me just use blue here. Let's call this acid compound A, B, and I'm going to call the base compound C, D. And all I'm saying is A is the positive, B is the negative ion in the acid. C is the positive, D is the negative ion, just general letters so I can kind of remember the chemistry. It says these two positive ions exchange places. A double replacement pattern. Exchange the positive ions. And so A goes to D and C will partner with B. So on the product side, we know that we always have to write the positive ions first. So here I'll have positive ion A, but now hooked to the negative ion D. And I'll have A goes to D, and then the next one I'll write is plus C going with the negative ion B. We've produced a salt and a water. So highlight that in this way. Here's the carboxylic acid positive ion part, the COO, and then the H. And this, I'm going to erase that. This part here is the positive ion. So the positive ion in this particular acid is the proton right here. Okay, so thanks for adjusting that with me. And then I'll go back and highlight this portion of the compound in green and reminding you that that is the anion. So we have the positive proton and the negative anion components of that acetic acid. And here, of course, they're showing us that NaOH is a +1 and an OH negative. The two positive ions exchange places. All right, so the two positives exchanging places places an H on the OH. There's your water. And then, of course, the sodium ion will migrate to the negative ion here, and we create a salt called sodium acetate. Acetic acid, named as a salt, is called sodium acetate. I want you to say the positive's name first, and then to name the last name, the ic from the acetic acid gets converted to ate. So instead of saying acetic, we say acetate. So that salt would be named sodium acetate. So there is our acid-base chemistry where we have a transfer of a proton creating conjugate pairs. The salts of acidic carboxylic acids are water soluble. So in terms of, let me flip my page, make sure we're getting our notes together. The salts are water soluble, but the carboxylic acid itself is not water soluble. So we're turning this water insoluble acid, the acid being insoluble, and when we take it and turn it into an ionic compound, we've tainted it into a water soluble salt. And let's emphasize that this is now ionic. That's the general term for ionic compounds are called salts. We turned an insoluble acid, and remember that general rule is about 6 carbons or less. Let me write that because we wrote it early in our notes. 6 carbons or less are water soluble, but greater than 6 carbons are not. And I emphasize that because look at this example here. We have octanoic acid. Octane is 8 carbons in the chain, so octanoic acid would be water insoluble. If I wanted to convert that to a soluble substance, I do an acid-base reaction. Acid plus base makes a salt and a water, and therefore I've produced a salt. Practice the name with me. The salt's name, say the name of the positive ion first, sodium. And then the ic part of the salt, not the oic, let's emphasize that, but just the ic part gets turned to 8. So you keep the O in this word, octano, and then to end it with an 8. Octanoate is the ending for that salt. We'll keep practicing. All of these words sound funny to us at first. So these carboxylic acids undergo a neutralization with a base, producing a salt and a water. And part of our learning goal is to name the salts. So to name the metal salt, we've practiced saying the name of the positive metal ion first, then the parent, and then 8 as the answer. So by the parent is the carboxylic acid name. So the last part of the acid is ic. It turns to 8. So let's practice here. This, as a carboxylic acid, just to remind ourselves, would be called acetate. And so its salt would be called sodium acetate. So this would be acetic acid turning to acetate, ic to 8. Here we have 3 carbons. The acid itself would be called propanoic acid. Take the ic and turn it to 8. So the anion would turn into propanoate. Notice that I'm only removing the ic, not the O with it. The O stays with it. But over here, remember, there was no oxygen, so it just says acetate or propanoate is the last name of that negative anion, potassium propanoate. Let's practice. So I'm going to ask that you pause the video and try this problem on your own. Take that propanoic acid and draw it. React it with potassium hydroxide. Show the formation of the salt and the water during an acid-base neutralization reaction. And then try naming the salt. Practice first. And when you're ready, turn the video back on and we'll practice together and give you feedback. All right, your video is started again. I sure hope you've practiced because that's where the learning will deepen. We're doing an acid-base neutralization where we know that an acid reacts with a base to produce a salt with water. The first thing we'll do is to draw the structure of propanoic acid. This acid will have 3 carbons, where the proton is this guy right there, propanoic acid. And it's reacting with a base of potassium, who's a +1, hydroxide, -1. So here's the base ion. The OH negative is the base. In a double replacement pattern, we're going to switch the 2 positive ions. So this positive acid hydrogen will now go to the hydroxide negative ion, and we will form water. The salt that forms has the positive potassium attaching to the negative region of the oxygen, and we would write that as our 3 carbons, O, and then the double bond for carbonyl attached to this oxygen, And this oxygen is negative and K is positive. So you can see that it's an ionic compound, commonly called a salt. We need to name the salt, which we just practiced on the previous page. We'll say the name of the positive metal first, and so it becomes potassium. Saying the name of the parent carboxylic acid, this was propanoic. The ic turns to 8, and we've named this as potassium propanoate. You've got a next series of problems that say practice these acid-base reactions and write out the salt and the water that forms on the product side. And we'll also practice naming. Turn off the video and try letter A and B, and when ready, come back to me and check your work. Okay, welcome back. Why don't we take a peek at this product? Here we have the sodium and the hydroxide as our base, and the carboxylic acid, the COOH, with the cyclohexane. So the cyclohexane-oic acid, just to practice our naming, cyclohexane is here, and then as it's a substituent group, it would be properly named with a YL, cyclohexanyl. And then, of course, this being the functional group of the carboxylic acid, COOH. And as I kind of finish drawing this, oops, that didn't come out right. Let me make that better. There we go. The C double bond O is now negative, and the salt then, Na plus, that's our formation there. I'm sorry, I hit that wrong button, salt. And of course the water molecule that forms as well. I forgot to finish this. That the carbon there would be formic acid. I am going to purposefully erase this name and not confuse this with this structure. This is a type of structure that undergoes some special conditions, and I won't emphasize that. These are the types of structures that are simple, straightforward, and that I'll emphasize on the test for naming. But the salt then that forms has the oxygen negative, Na plus, and a water. Now here in letter B, this one was a little challenging because you see that there's 2 sodiums and the carbonate is actually a -2. So if you remember your crisscross rules, when sodium is a +1 and carbonate is a -2, to balance the charges, you can see that there is a 2 needed for a subscript, sodium carbonate. But here I can see that there's only 1 hydrogen. And so part of this game was recognizing we need to balance the equation. It's going to take a coefficient of 2 acids to react with this 1 molecule of base. And let's model how. Over here, when the hydrogen attaches to the carbonate, H is a +1. Carbonate is a -2, so we need 2 units to balance that electrically. And then here, Na2, this would be the H2CO3, which is just a little different than making the water because we had a different anion. We had carbonate. And so now when I go that there's 1, 2, 3, 4, 1, 2, 3, 4. This would be called butanoic acid. This O has an Na, but I still have to remind you that there's 2 of them to balance the equation. So the coefficient of 2 to 1 forms the way that I have it here. The salt would be written first, 2 salts, +1 H2CO3. 2 units of butanoic acid. plus 1 unit of sodium carbonate will form 2 units of our salt and 1 unit of carbonic acid, H2CO3. We can practice naming this butanoic. The ic turns to 8, and the name of this salt would be sodium butanoate for the salt name. And let's remind ourselves what we practiced with about solubility in water. Remember the general rule, 6 carbons or less make it soluble. Greater than 6 carbons are insoluble, and salts are always soluble. So as we really are just labeling what type of compound we have here, I can see that I have an acid, the carboxylic acid functional group right here. And clearly this has more than 6 carbons in a chain, so this is insoluble. And my reasoning is greater than 6 carbons. How did you label the second? We have this O negative, Na plus. You recognize that as a salt, and salts are always soluble. I dash. And here we have a carboxylic acid, but the number of carbons is less than 6, so this is also soluble. That's my puppy wanting in. How about naming these salts? Are we practiced enough? Try these out and let's try them and get a common answer here. I have 1, 2 carbons. The common name for the carboxylic acid is acetic acid. Just to kind of emphasize how we're naming from the parent acid. The parent acid is acetic acid. So we name the positive ion first, and that positive, I wrote the word positive, I was saying sodium, and then take the ic and turn it to 8. This is sodium acetate. 1, 2, 3 carbons. So the parent acid has 3 carbons. It would be called propanoic. The ic turns to 8, and we would have the salt named potassium propanoate. How'd you do? You're doing well, I know. We're ready to flip the page again. Let's look at a second type of reaction, the next type of reaction past acid-base chemistry, and it's called substitution. Now we've practiced substitutions with other functional groups. Notice here on my carbonyl group, C double bond O, we have something that could be an acid, an ester, or an amide. So whatever Z is, if Z is an OH, we know it's a carboxylic acid. If Z is an OR, we know to name that as an ester. And if Z has the nitrogen in place of the oxygen, we've learned to label that as an amide. In the presence of a reactant, we can substitute the functional group of the acid or the ester or the amide with something else. And the Y could be turning into an OH, OR, or NR2. The Y and the Z exchange places. So here's the Z now connected to the H, and we see that exchange occurring. These two just simply exchange places. Let's give something a little more concrete than the general formula. The general formula for the substitution reaction on 17.8 is what we just diagrammed here, but it might be easier to see some examples. Reaction 1. This is a carboxylic acid reacting with an alcohol to form an ester, and we're asked to draw this general pattern next. So our carboxylic acid, we're going to start by recognizing the COOH, but what's getting exchanged is the OH part of the functional group. And this time when we react it with an alcohol, the alcohol functional group we know is that hydroxyl group. The hydroxyl group we want to emphasize is the OH bond that is going to be broken, and that is the form where the OH and the OR will exchange places. So for instance, let's say that this is ethanol. Just to put in an example, if that is ethanol, now we can see this R group is representing those two carbons. But where the bond will break is right here between the oxygen and the hydrogen. The OH on the acid and the OR from the alcohol exchange places. So now we have water produced and an ester comes out. We have exchanged a carboxylic acid into an ester by a substitution reaction. And to do that requires the use of an alcohol. We can begin with the carboxylic acid and react it with a nitrogen group, an amine. And if all the hydrogens in an amine saturate the nitrogen, it's called ammonia. So again, an amine that has all the hydrogens connected in all three bonding directions of nitrogen has a name that's probably familiar to us called ammonia. But again, what's happening is we're breaking one of the bonds in an NH3 molecule, and we're going to exchange the OH and the amine group to create an amide. The amide is formed along with a water molecule through this substitution reaction. Let's focus in on something. We just drew a general form, and now let's try some more specific reactions. Let's practice, it says on your page. I'm going to review back to reaction 1, a carboxylic acid plus an alcohol. So here's our carboxylic acid. This carboxylic acid has 3 carbons. So this is propanoic acid. We're reacting it with an alcohol, and the alcohol has 1 carbon, so we've learned to name it with the OL ending. This would be called methanol. And here we have an acid catalyst. Alrighty, so we have propanoic acid, carboxylic group. We have methanol, which is an alcohol. And I want you to notice it's right here between the O and the H that the bond breaks. So the substitution will occur with the OCH3 from the alcohol, with the OH from the carboxylic acid. We want to simply exchange their place. So what forms is a new CO bond. The carboxylic acid has turned into an ester. There is 1 carbon after the oxygen, so it's called methyl. There is 1, 2, 3 carbons connected there to the C double bond O. Propane O8. That's the name of our ester. And of course, water is the byproduct of this reaction. There is a fancy vocabulary word for this type of reaction. It is known as a Fischer esterification. Notice that is not the same spelling as the Fischer projections. Earlier in our course, we did Fischer projections, and it had it went SCH. So it is just a little bit different spelling. So it's not the same person. But a Fischer esterification has us taking an alcohol and a carboxylic acid to convert it into an ester and water, a substitution reaction. Let's try another. We have to flip the page again, trying another Fischer esterification. This time it asks us to try one with benzoic acid. Now this is a common name we're trying to learn, benzoic acid. C double bond OOH is our acid. And we're going to use methanol again. Methanol has one carbon as the alcohol. So we have a carboxylic acid. And we're reacting it with an alcohol. And when we do so, we produce an ester and water. And really, it's just nothing more than a substitution reaction. We're going to take the H and the OH to form the water. And we take, let me highlight this, we'll take the OCH3 and the OH and exchange their places. So on to the original carboxylic acid, the new functional group will become OCH3. Methyl benzoate and water. This process of converting the OH into an ester group is known as Fischer esterification, and it is in a dynamic equilibrium, and you can manipulate the conditions according to Le Chatelier's principle. For instance, if we used excess alcohol, the stress becomes increasing the alcohol. We want to alleviate that stress, so we shift away. It would produce even more methyl benzoate. If we removed water, that's the stress. If you decrease the concentration of a product, you want to make more, so that would also influence the product side. So just an application of Le Chatelier. Try some on your own. We're going to use ethanol in the presence of sulfuric acid. Ethanol is a 2-carbon chain, so the alcohol would have 2 carbons in its chain, CH3, CH2, OH. What will that make? In a Fischer esterification reaction, predict the products. Notice that we're always forming a water, and that's by taking the proton here with the OH here. That combines to make your water molecule. Leaving the OCC to go onto the OH original group. So here we have CH3 taken twice, CH. Here's our carbonyl carbon. And they're reminding us of that 120-degree bond angle. It's a trigonal planar geometry. And now placed here, I got to remove the water, make room, would be the OCC from the alcohol. Looking here, we're going to add the alcohol, same one again, the ethanol. So we have the OH, CH2, CH3. That is a formula for ethanol. OL is the alcohol. We know to take the OH and the H, and we combine them to make water. So we always know a byproduct of ester, of producing the ester, is a water molecule. And then we're converting the carboxylic acid. It started as CH3. And then in parentheses, we had CH2 taken 6 times, carbonyl carbon. And then here, the OCC from the alcohol. This is a 7, so this would be ethyl heptane O8 would be the name of that particular salt. And one more, here's the cool right here. Here's that cyclohexane. Here's the carbonyl carbon. Adding an ethanol molecule says let's take off the OH group and combine it with the hydrogen to make a water. And in its place goes the alcohol OCC. We're getting the pattern. You keep repeating. The repetition is your friend while you're learning. And those are the answers that we just did. So those are the clean copied answers of all of those that we mentioned. So letter A, B, and C from the previous page all cleaned up for you so you can see them in book form. But it really is the same as what we drew over here. You can verify with that picture if you'd like by pausing the video. Now let's go back to that second pattern of reaction where we were looking at carboxylic acids reacting with ammonia to make an amide. So instead of the alcohol, we're using a source of nitrogen. So converting carboxylic acids into an amide requires a nitrogen. And here we have, if you remember, the nitrogen, of course, has a lone pair of electrons, so it has 3 spots for bonding. Those 3 spots for bonding can be to hydrogens or to carbons. It does not matter. We're just reacting it with a nitrogen group. Whatever it's substituted on doesn't matter. And remember how we practiced a nitrogen can be primary, secondary, or tertiary. It depends on how many nitrogens it's attached to. So in this general formula, you're writing out these R groups represent carbons, carbon chains. So this would be known as a secondary alkyl or a secondary nitrogen. But the pattern will be the same, except this time we're going to take the OH group off and substitute with it the product to create the amide. So our general formula says taking a nitrogen derivative and exchanging its place with the OH to form the amide and water. Let's practice more specifically. Here we have ammonia, NH3. So if I look at that structure, NH3, one of those NH bonds is going to break. And remember that a hydrogen and the OH from the acid combine to make water. So that's still there. There is a water molecule being lost. The spot where the OH was then gets replaced with the NH2 group, and we've created a primary amide. Primary because this nitrogen is attached to just one other carbon. We could create secondary or tertiary amides as well. When we look at acetic acid with methylamine, acetic acid has 2 carbons in the formula, acetic acid. Here's the nitrogen. Notice that it's attached to just one other carbon at this point, so it's named methylamine. Methylamine then, when it goes on, this hydrogen and the OH here combine to make the water. Don't forget that that's always a byproduct. Sometimes the screens will leave it off, but we know that it's being formed. And then, of course, this entire structure will go on in the place of the OH group. And this time we have formed a secondary amide. Because this nitrogen is attached to 2 other carbons, we called it secondary. So just to clarify how that would look, the nitrogen is attached directly. You have a carbon coming down and a hydrogen going off the other direction. So that's why it's called a secondary amine. It's attached to 2 other carbons. And in the next example, we can create what's called a tertiary amide by using a substrate such as dimethylamine. So again, using a simple acid such as acetic acid. And this time we're using a secondary amine, because it's not attached to the C double bond O. The language is INE. We know to take the H and the OH, and it will combine to make a water. And then we understand that this part of the structure from the amine will replace the OH group from the acid. And here, the NCH3 taken twice can also be drawn as the original structure. We have a nitrogen then attached to two other carbons, and therefore is now called a tertiary amine, tertiary amide. Good. All right, great. Let's practice. We're doing so well. Home stretch here. Let's try some of these. Here we have ammonia in letter A. The acid is going to start with 1, 2, 3, 4, 5 carbons. Alrighty. So for letter A, my initial acid has 1, 2, 3, 4, 5 carbons. And I'm going to react it with NH3. And so let's just keep in mind that the process, just drawing it out for the visual. I'm going to break one nitrogen to hydrogen bond, right? And I'm going to make a water molecule from it. So I know that water always comes out. And I understand that what's left over after I take one hydrogen off will replace the OH group from the original carboxylic acid. So in the end, the structure has 5 carbons. 1, 2, 3, 4, 5. The double bond O, and now an amide has formed. Let's look at letter B. We start with the same carboxylic acid, 5 carbons, 1, 2, 3, 4, 5. So the double bond O, OH. And this time we're reacting it with a nitrogen that has 1 hydrogen and a methyl group attached in the other direction. All right, see how what I've done? We have 1 hydrogen and 2 units of CH3. I know nitrogen always has 3 bonds. 2 of those 3 are carbons and 1 is the hydrogen. It's the hydrogen and the OH from the carboxylic acid that go on to make the water. And the other product will be where we have what's remaining take the place of the OH. And so our product, there's our 5 carbons, the double bond O, and now in its place will be a nitrogen attached to 2 methyls. We made a tertiary amide. And finally in letter C, I'll have room right here. I squish it in. Here's the original 5 carbon acid, COO. And now the oxygen is going to get replaced. And look at what's going to happen. Look at this substrate here. You have a carbon to a nitrogen attached to 2 hydrogens. Just structurally, that's what this reagent looks like. We're going to remove one of the hydrogens to make water, leaving me N, 1 more H, and the methyl group. This guy is called a secondary amide. So letter A made a primary, letter B made a tertiary, and letter C made a secondary amide. Pause the video and just take a look at the answers. I have them on a series of slides. I'm going to show you, and just pause and make sure that you see that they are matching what you have on your paper. Here's letter A and B. I'll just pause, give you a moment. Notice we have the same 5 carbons that originally came from pentanoic acid. Just giving you time to process here. And then now let me share with you the letters C and D. They should match your paper. The original 5 carbon. You know what I did, and it's just kind of an aha moment. I went A, B, D, and I skipped letter C. I bet you caught that, and I'm just catching the bus up. I'm sorry. You try that with letter C. I never drew it, but I can share with you what would have happened there. Letter C is shown here, that the substrate here, the nitrogen, still has that cyclohexane group and 1 hydrogen. The other hydrogen was removed to make the water molecule from the acid. I'll just give a smiley face so I know you did it anyway. All right, we have a next category of reaction, but we are indeed in the home stretch. You're doing so well. Way to hang with me. We have here now the reaction of an ester and amide of a hydrolysis reaction. Friends, the good news is that everything we just learned is just looking at it from the opposite direction. A moment ago, we said an alcohol plus an acid will make an ester plus water. We literally just said that in ester hydrolysis. We called it a Fischer esterification. And here we said an amine plus a carboxylic acid will form water and an amide. We literally just finished those practices. The good news is that the last part of the chemistry is saying, okay, what if we read it in the other direction? If we read it in this direction, it's the ester plus water gives me back the original stuff, the acid and the alcohol. So they're reversible reactions. I can add in water and get back the acid. So this overall driving force is to get the acid back from the original product. And so as you look at the general formula, that general formula there is just asking us to go in and show water hydrolysis. General formula of ester hydrolysis, right here. The general formula of amide hydrolysis, right here. And then we'll practice one. The amide and water gives me the acid and amine. The ester and water gives me back the acid and alcohol. You're adding the HOH back to the group. And then that third box of your notes is saying, well, let's try one specifically. Here is a molecule that we have named ethyl propane 08. This is the name of an ester. We practiced that earlier in our chapter. The ethyl propane 08. So ask yourself, what was the original carboxylic acid and what was the original alcohol? And you'll have predicted the two products. So in this reaction, notice that the H and the OH break back apart, and these guys just go back to switching partners. So the original acid came from the name propanoate. The acid would be called propanoic acid. And this section came from the alcohol. So if this was the acid, we made propanoic acid. If this part came from the alcohol, we know to make ethane-ol, the OL for the alcohol. We're just driving it in equilibrium, one direction or the other. Esterification this way, hydrolysis this way. Esterification in the forward. Well, that's not right because I wrote the reaction the other direction. In this direction, we're adding water in this particular, so that's hydrolysis. And if I read it in the other direction, where I add the alcohol to the acid to get the ester, we call that esterification. We've got some practices. With our practices, it gives us letter A, B, and C, and it's asking us to predict the products for each. And so as we digest this, find your carboxylic acid part and find the alcohol portion. And the remainder is easy. You're starting with the ester and you're treating it with water. So the ester with water is known as hydrolysis. Highlighted here is the green original acid. So I just simply rewrite everything that is given to me on this portion of the molecule and end it with OH. There is a total of 1 plus 8 is 9 plus 1 more. There's 10 carbons here. So that would be decanoic acid. And on this particular spot, there was one carbon there. And so this would be called methanol, the alcohol ending. The letter B, here is the acid portion, and here is the alcohol portion. And so as we begin writing the carboxylic acid, there's 4 carbons. So I see 1, 2, 3, 4. On carbon 3, there is a methyl group. So this would be 3-methyl-butanoic acid. And on the alcohol portion, there's 2 carbons. And so the alcohol becomes ethanol. In letter C, recognize where the C double bond O is, right here. C double bond O. It didn't draw it out, but we see that with that CO2. So right here becomes the carboxylic acid, and you can see the carboxylic acid then just adds the OH to that original structure. Here is the alcohol portion, and so we had 1, 2, 3. So 1, 2, 3, that is called propanol. Not too bad. And then equal treatment with the amides. Of course, the amides are exactly the same way as the esters. If we add water to the amide, we get back the original amine salt. And so here's the reaction that it's asked us to draw in that general formula. An amide plus water in the presence of an acid catalyst, and that's what we're recognizing here on the arrow, the acid catalyst of HCl. Notice the OH from the water molecule goes back to form the original carboxylic acid, and the NH, this part of the amine group, ends up to be the salt, and that's the role of the what we'll say is the role of the catalyst there. The chloride creates an electrically neutral compound based on charge. So chlorides being negative, nitrogen has a formal charge of +1. So you can get back the original carboxylic acid and the amine salt through the process of hydrolysis. And we can take a closer look here, where we add an amide to water in the presence of a base. In the presence of a base such as sodium hydroxide. Now let me go back one slide to emphasize the difference. This slide was all about acid catalyst. Have I emphasized that enough, that this is the acid catalyst sitting on the arrow, and it produces the salt with the carboxylic acid? But when I flip the page here, and now in the second, it clearly says with a basic catalyst, that amide turns the carboxylic acid into the ion, and what's neutral is the ammonia. In the presence of a base, the carboxylic acid is left unprotonated, and you create a carboxylate negative or anion and the neutral ammonia. Compare and contrast that. In an acid catalyst, the neutral molecule is the acid, and the amine is the charged salt. But in a basic solution, in a basic catalyzed solution, the charged ion is on the acid. So the acid is charged as O negative anion, and the neutral molecule then becomes the ammonia. In the acid, it makes neutral acid. In the base, it creates a neutral base. Ammonia is the base here. So what would that look like for practice? All right. What are the products formed when we're treating water and an acid catalyst? Acid catalyst. So just a note that the acid catalyst makes the carboxylic acid neutral. So recognize where the carboxylic acid will form, and our product will be, you know what, I can't read that now. That's an 8. So I have CH3 parentheses, CH2 taken 8 times before I finally get to the carbonyl carbon. The nitrogen is going to be replaced into a neutral carboxylic acid. There's 1 plus 8 plus 1 more. That's decanoic acid. And the salt that would form would be a charged ion. And with the acid being H2SO4, just reminding you that the negative ion is what was attached to that positive charge there. So just to kind of remind you, that negative ion there of sulfate is just kind of hanging out next to this. So you'd have SO4 minus 2. It had, 2 hydrogens on it. So you'd add 1 more and make this a positive charge. Letter B. Here's the acid component. And so the carboxylic acid in an acid solution becomes neutral. We have 1, 2, 3, 4. And on carbon number 3 is a methyl group. So there is the backbone of our letter B carboxylic acid. Finish off the structure. That is 3-methyl butanoic acid. And this time the nitrogen would have a methyl group associated with it and have that positive formal charge, left with the sulfate nearby. Whoops, I forgot one of these. And here I'm recognizing a tertiary amide, and on this side we have the acid. So the carboxylic acid ends up neutral in an acid solution. I form the carboxylic acid, and this time the nitrogen has 1, 2, 3 in both directions. So I have 1, 2, 3, 1, 2, 3. A hydrogen gives me a +1 formal charge, and the sulfate negative would be close by. Those are called salts. And now the same question, but this time it's asking us to treat those same products or those same reactants, but this time with NaOH, sodium hydroxide. And so let me just add a slide. And I'll just, well, here, I got this. Oh, so yeah, I forgot. So here's an example where you can take a moment and just see the structures that we drew kind of cleaned up. So take a moment and pause if you'd like and just study what we wrote earlier and make sure it's matching yours. For example, in this one, I wrote hydrogens in all directions. That was my NH4 plus, and I did it this way. And then I just put the sulfate around it. So that's fine, either direction. And then when you're ready, we'll go forward there, but certainly pause if you want more time. And we'll tackle what happens if you treat it with a base. And so now when I see base, the base is neutral, and the base is the amine. And so we're going to create a negative carboxylate ion. So let me model one. Again, I'm going to just find the carbonyl and notice that that will become the carboxylate ion. So we'd have CH3, parentheses, CH2 taken 8 times, C double bond O. But now in a base solution, this remains negatively charged. And if it's negatively charged, the positive ion will be attracted to it. The NaOH will have the sodium kind of migrate over to the negative charge. And of course, now, here's the NH2 group that when I take it apart, it ends up to be the neutral molecule NH3, ammonia. Remember, there's a lone pair up here now. Find the carbonyl group, and that becomes the acid. So here's one we counted 1, 2, 3, 4. We had 3 methyl butanoic acid. So I'm going to draw my 4 carbons, put the methyl there, and there's the carbonyl. But I know it's going to be left negative, and then therefore the sodium will migrate. Here is the base part of the group. So the other product will have N attached to an H, attached to a methyl, attached to the other hydrogen with a lone pair of electrons. It will be the neutral compound. And in your last example, here's your cyclohexane attached to the carbonyl carbon, left as a negative ion, and the sodium will migrate over, creating a neutral compound. Here is the amine portion when it's separated out. Nitrogen will be attached to 3 carbons in either direction, leaving a spot, that's kind of crowded in there, for 1 more hydrogen to complete its octet. And then again, let me share with you just the cleaned up copies, just so you can compare your structures that we just drew. Emphasizing that the base is the neutral compound and the acid is now the salt in a base catalyzed reaction. I think you did it. We're going to end our video notes here. I'm so super proud of you. Come to class on the next class day all ready for some practice. We'll put our practice to use.